Okay, well, I just recorded a perfect take. Everything was just right about waves, but then managed to delete it. So, we're starting over again for take 2 on the wave basics. There are lots of things to know about waves. We're going to just barely skim the surface of all the things there are to know about ocean waves. There are 2 excellent chapters in the Wunsch book on waves, talking about how they're observed, what they look like, different kinds of waves. Today we're just going to get some of the basic concepts of what a wave is, how it propagates, how to describe it, some of the key quantities that we might measure or just explain about it. So what is a wave? First question, revisiting inertial oscillations, seeing if that satisfies the definition of a wave. Then we're going to get this key concept of dispersive and non-dispersive waves, which is closely related to the concepts of group and phase velocity, or group velocity and phase speed. And then we're going to touch on the end of some of the rotation effects on waves, which is going to be the topic as we think about large-scale waves that are strongly affected by the rotation of the Earth. So what is a wave? Well, maybe you can think about what a wave is not. They are not crests, not those high parts above the water that are moving. That's just part of the wave. They're not sinusoidal necessarily. There are packets of waves, a fixed number of crests and troughs. And the group velocity and phase speed is related. The group velocity is related to the propagation of the packets. The phase speed is related to the propagation of the crests and troughs. Waves of the beach are one particular kind of wave, surface gravity waves, that vary whether they're in deep water or shallow water. Cool things to talk about, we're going to talk about next week. Rogue waves, tsunamis, those are kinds of surface gravity waves. So oceanographers like to categorize the waves by where they are, surface gravity waves are at the surface, and what the restoring force is. Gravity is the restoring force for a surface gravity wave. Cool. Okay. So from a mathematical perspective, this is a great book called by Witham on waves. And he defines a wave as a recognizable signal transferred from one part of the medium to another with a recognizable velocity of propagation. Pretty vague. Waves occur in many different kinds of media and take on many different forms. We can often think of waves as simple sinusoidal undulations, but that's too restrictive and not very useful. Kundu has a nice definition. Waves are the means by which information is transmitted between 2 points in space and time without movement between the points. So he clarifies without movement between, because what's the difference between a wave and a current in that case? A current going from point A to point B also transfers information and covering space and time, but it moves the fluid with it. The wave just moves the fluid, but it doesn't move the fluid from point A to point B in order to transmit the signal. The wave is information connected through the motions of the fluid, but not propagating with the motion of the fluid. Key distinction. There's some better examples of waves. So we talked about waves on the beach, but processes that lead up to El Nino are also waves. Rossby and Kelvin waves are important examples that we're going to talk about. Sound is a wave in the pressure and density of air or water. Phone calls are an interesting kind of wave. They're a wave that has both a sound aspect and then also a radio aspect if you're thinking of a cell phone. And interestingly, probably a conversion through a digital to analog converter as well. But information is propagating first through the air, then into the microphone, then into the D to A converter, then out into the radio as a digital signal, then into the other end, converted back into sound. Pretty cool. The radio is obviously part of that. Epilepsy is a wave. It's a wave within your brain waves. It's a particular kind of, an epileptic seizure is a particular kind of wave-like pattern within the brain. Traffic jams are actually a wave. We can talk more about that when we have a better handle on phase speed and group velocity, but traffic jams actually have the tendency to propagate upstream in the direction of flow of traffic, which is a very confusing thing. You sometimes run into a kind of ghost traffic jam. You can't figure out what caused it. Actually, the event that caused it was farther down the road, and it's propagated like a wave backwards up against the traffic. The aurora borealis, lots of other things are waves. So this is a great joke, which I will leave you to read. I hope you've already read it, but in the interest of time, jump ahead. Okay, inertial oscillations. Remember what these are? These are the little wobbles that happen on the die. In this rotating tank case, most of the motion is going in Taylor columns or curtains of flow, but then the curtains are wobbling back and forth. And as they wobble back and forth, it's with a period that's locked to the rotation rate of the table. We talked about this before. Let's jump over the equations. We talked about these being the equations, so we just keep the time tendency and the Coriolis force, nothing else. Notice that the U is here in this equation and then here in this equation. The V is here in this equation and then here in this equation. So these are two coupled equations. Can't solve one without the other, but you can eliminate the U by, say, solving this one for U, plug it in there, and you get a second order ordinary differential equation in time. You can solve that ordinary differential equation with this solution. Cool. Sines and cosines. Great. Is that a wave? It's probably not a wave because it doesn't have any x's and y's in it. It's just an oscillation in time, but it does not propagate like all of those definitions we said. Propagation speed, propagate from point A to point B, doesn't do it. There is actually something called an inertia gravity wave, which is a coupling between a gravity wave and an inertial oscillation that does propagate in time and space. Cool. Okay, I started using some terminology without defining it. Let's be a little more careful. The crest is the high part of a wave. The trough is the low part. The wavelength is the distance from crest to crest or trough to trough. If this is the direction of the wave's propagation, you might have some overturning, some motion underneath the wave of the water. It's called the orbital path. So if I put a particle in there, it would go around and around in a circle like this. Sometimes it's called the orbital velocity. This motion of the water underneath the wave is not the motion that causes the wave from, well, it is the motion that's related to the wave moving by, but this velocity is not the speed of the propagation of the crests. Instead, what's happening is that you're converging back on the back end, lifting up the trough, and diverging and pushing down the crest. So it's a information propagation, not a current that is carried by a particular motion of the medium underneath. The frequency is the number of waves passing a particular point in space each second. The period is the time required for the wave crest at point A to travel one wavelength, or additionally the time sitting at one place to wait for the next crest to arrive at that same point. There's also something called the wave number, which is the number of crests within a given distance. So just like the frequency is the number of wave crests passing point A in a unit of time, the wave number is the number of wave crests in a unit distance. It's related to the wavelength, the same way that the frequency is related to the period. Okay, let's take a look at this little movie. So this is kind of illustrating frequency as the crests go by. We're at a high. Now we're at a high one period later. Now we're at a high another period later. So if we counted the number of crests we were crossing per unit time, we would get the frequency. That's the deal. The phase speed is the speed at which this crest or this trough, which are called, those are particular phases of the wave as it goes from crest to trough to crest. Those are the phases of the wave. The phase speed is the speed at which each phase propagates. And if you think about it for a little while, you'll see that the frequency times the wavelength is equal to the phase speed. Okay, what's an equation that, unlike the inertial oscillations, actually does have a solution that is a wave? Well, here's the most basic wave equation. It's the linear non-dispersive wave equation for a unidirectional wave. So here we're just looking at 1D in x. C is a constant. Eta is some wave property. Could be height, could be temperature, could be vorticity, whatever, it doesn't matter. This is something that's propagating. This has the ability to propagate. And you might say, well, what if I plug in sines and cosines and I can figure out how to get that to work? Yeah, sure. There's a much more general version, a solution to this equation possible if C is a constant. And here it is. Take any old function you want and just make it a function of only x minus ct, and it solves this equation. That might be surprising. It's basically a clean application of the chain rule. If I take this and plug it into here, I get the derivative of eta times the derivative of its argument. So the derivative of eta is just eta prime, whatever its derivative is. The derivative of the argument is minus, with respect to time, is minus c. So I get minus c eta prime x minus ct. And then this one, I get plus c for free because it's already in the equation. Then I take d eta dx, which gives me eta prime. No additional factors on x, so it's eta prime. So these two cancel for whatever differentiable function eta you want to stick in here. But you might have noticed if as time goes up, x needs to go up as well. That means that this is a rightward propagating wave propagating towards positive x in time. Can't propagate left. Doesn't do that. So this equation is a little bit too simple. We might want, what happens if we want waves that could go in both directions? That's this equation. So now we could see that if we plug in that same style of solution, we get one rightward propagating one, eta plus, and one leftward propagating one, eta minus. So as in this one, as time goes up, x gets more and more negative, and this one, as time goes up, x gets more and more positive in order to track the same feature in this function. What does this look like? Here's a nice triangle to begin with. There's a leftward propagating part, rightward propagating part. Triangles just propagate. Don't change their shape. Could have put any other weird shape in there you wanted. Would have been the same story. So a plane wave will be useful when we talk about dispersive waves. And the plane wave makes the analogy between sinusoidal stuff and, well, not the analogy, the formalism between sinusoids and this arbitrary function eta. So if we think of the Fourier transform of eta, which unfortunately should have a dk here rather than a dx, we could say there's an amplitude for each wave number times a propagating wave function, e to the ikx minus omega t. That looks a little unfamiliar, but if I factor out the k, I'd have x minus omega over k. So omega over k apparently is equal to c. This is the wave-like bit. This is the other bit. If we don't know the sign of omega versus k, we could have leftward and rightward propagating waves in this same formulation. If this is a complex amplitude, we could have sines and cosines represented by this. We have a real part out here which sorts all that back out. So we could transform any old function we like this. And so if we take only one of the constituent frequencies from this integral over all of the, k's, we get a plane wave. And so the plane wave is a solution to this wave equation for the specific values of omega and k that obey this relationship. Omega squared equals c squared k squared. The squared means we can go left and right. C is the phase speed, the speed at which the crests propagate and troughs propagate. K is the wave number. Omega is the angular frequency. So if this is true, then I solve this equation, which means that basically all of these waves are propagating. They all have the same c, which is just omega over k, plus or minus omega over k. This kind of a function is called the dispersion relation. It relates the frequency to the wave number. If you don't remember your sines and cosines, go check out this slide. Check out the appendix of watch. Okay, phase and amplitude. This part is called the amplitude part. This part is called the phase part. So you can sometimes written like this. Here's the amplitude function, which could be a function of wave number. It could also be a function of space on a slower, like kind of a envelope function. And then the phase is the part that varies rapidly like this, and that's this guy up here, which has this kx plus or minus ct if you want to factor out the k, or you can multiply kx plus or minus omega t if you wanted to bring the k in, remembering that k times c is equal to omega for at least a non-dispersive wave. Okay, we've been skimming along using sines and cosines without really dealing with the 2 pi's. There's a whole nightmare of 2 pi's are all around all over the place because in order for this function inside the phase to reset, this e to the I theta, theta needs to go from 0 to 2 pi, not from 0 to 1. So kx minus omega t resets at 2 pi, not resetting at 1, which means that you at 1, here's the angular frequency times time will reset itself every 2 pi times an integer, which means that the period is 2 pi over omega, not 1 over f. And the real frequency, that is the thing that's 1 over the period, is omega over 2 pi. Same thing is true if you do wavelengths and wave numbers. You got to crank through, keep track of the 2 pi's. Okay. We don't need to cover that again. So here's some more. So now we've got this amplitude function. We've got the phase, which is in radians or dimensionless. We've got the angular frequency, which is radians per unit time. We've got the true frequency, which is cycles per time or just 1 per time. Period, which is 1 over the true frequency. The wave number, radians per unit length. The wavelength is a length, which is 2 pi over the wave number. All right, dispersive and non-dispersive waves. If it is true that the phase speed is just equal to omega over k for all k's, that is if the dispersion relation is just simple like this for some constant c, so that every k has the same c, then every constituent of the Fourier transform propagates at the same speed. So phase positions of different waves will stay together. If that isn't true, then different wave numbers will start to separate out. So let's look at a little movie and see what that looks like. Here's our non-dispersive wave propagating along. So the triangle stays a triangle as it propagates. No evidence of the different wavelengths that make up the triangle separating out. Here's the case if we use a square wave in a dispersive system. So this is a different kind of wave. It's a little bit dispersive. You can see that you're starting to see these sines and cosines separating out of the square wave as it propagates in time. The Fourier transform is revealing itself through the dispersion of the wave. Fourier transform is revealing itself. Waves always did this long before Fourier came up with the mathematical trick. The mathematical trick is just a good way to illustrate how that propagation is going to work. So one consequence of this is that getting into the business about how fast a wave is gets a little complicated. The wave group has a velocity, and then the phases, the crests and troughs, have a different speed that isn't necessarily the same as the velocity. So for a surface gravity wave in deep water, the phase speed is twice the group velocity. So as this group moves up, it goes from 8, 7, 6. The group is moving along. It's not moving as fast as this red marker. It's moving half as fast. Whereas this particular number 5 wave is propagating faster than the group. So it appears in the back of the group and disappears in the front. Just like 8 has disappeared after the second row, 7 has disappeared up here after the 5th row, 6 disappears, etc. Let's see what that looks like in a video. Here's a non-dispersive wave, which is a composition of a couple of different Fourier modes. Nothing's changing. Phase, group, all go on the same speed. Here's a dispersive wave. Same initial condition. Now you can see that the long waves are getting out front of the short waves. You can see that the phase of each crest is actually overtaking the group. So the crests, watch that again. Crests are appearing in the back of the group and disappearing in the front. See them disappearing, see them appearing from the back. And then it's a little bit easier to see in the the shorter wave where the disappearance is very fast and the appearance is very fast. Okay, so if c equals omega over k is our phase velocity, or phase speed maybe, what about group velocity? How do we find that? Well, it's actually just the derivative of the dispersion relation, the omega from the dispersion relation with respect to k. let's think about that for a second. If I move the k over to the left side of this equation, so I have k times c equals omega as my dispersion relation, with c being a constant, and I take d omega dk, then I would just have d omega dk equals the same old c. So for a non-dispersive wave, I actually have the group velocity equal to the phase speed. But that's what we already knew from this video. Everybody's moving the same speed. No surprise. This is just the math side. But what is a surprise is that this d omega dk actually gives you the speed of an envelope. And there's a derivation of this in Wunsch, which is a little bit hard to follow, but if you're interested in the mathematical details, that's that. At the end of these slides, there's also a derivation, which I'm not going to go into, but it's there for your reference if you want. So we can imagine this envelope with the phase wrapped up inside, and the propagation of the envelope is what's going with the group velocity. The propagation of the phases themselves inside is going with the phase speed. All right, I've been careful without saying it to talk about phase speed and group velocity, which takes a lot of training. And the reason why is because c in this form does not have to be a vector. In fact, it is not a vector. K is a vector, omega is a scalar. The ratio of a scalar over a vector is not a vector. The derivative of a scalar with respect to a vector is a vector. So the group velocity is actually a velocity. It is a vector, but phase speed is not. Let's see what that means. Imagine if this is waves and they're propagating in this direction where lambda is. So lambda, every frequency lambda goes from here to, it goes over that short distance. That's every period. The wave crest propagates that distance lambda. But now here to the side where it says apparent lambda, over the same period, the wave crest there has actually traveled quite a bit farther. So the phase speed in this apparent lambda direction is actually larger than in the lambda direction. That's totally opposite from what you get with a vector. A vector, the direction of propagation is the maximum. And then every angle away from that actually has a smaller amplitude because it's not, you have to dot product from the direction of propagation into whatever direction you're looking at for the component. Here, the off direction of propagation direction propagates faster. So this is not only cool, this is something that surfers know about and use all the time. So here's a little bit of video from Pipeline in the North Shore of Oahu, which is an amazing place to see. That's what the waves are like. So in the direction of propagation of the wave is actually not the fastest way to surf. If you want to go fast, you don't go down the wave, you go across the wave. So see, you start out going down the wave, which gives you a slow start, but then you turn, and actually when you turn, you don't slow down, you accelerate, because you're now trying to keep track of the phase speed in the direction along the wave, rather than the phase speed in the direction of propagation of the wave, which is slower than the one along the near perpendicular. There are lots of rocks at Pipeline, so you get worried about that, so you would like to go very, very fast and hopefully not fall. But there we go. That's enough about Pipeline. Okay, so take another look at this video. Long waves are getting out front, short waves are staying in the bottom. Phase speed is faster than the group velocity. It's overtaking. Cool. I think we got it. Here's the derivation from Wunsch about how you actually derive the group velocity is related to the derivative of the frequency with respect to the wave number. Here's another one from a Chapman and Rizzoli chapter, which is a free book online. I have it linked from our webpage if you want. This has lots and lots of great stuff about waves. This is one of the best books about waves ever written. It's actually a collection of notes put together by Dave Chapman and Paolo Rizzoli, based on their thesis advisor, Merle Hendershot's discussion about how he just understands waves. It's really, really great. Merle really understood waves better than anybody. This is a great set of notes. Okay. We have hinted at the fact that there could be lots of waves inside of these equations. It's because they're linear wave equations. So just like we had the linear equations for Ekman and geostrophy and inertial oscillations, just added them together, superposing the different solutions to get the total, we can do the same thing with different waves. We can add them on top of each other. One of the most interesting cases is the case of a standing wave, which is where you have one rightward propagating wave and one leftward propagating wave of the same amplitude. If you have that, you can do the collect the terms together and play your favorite exponential to cosine transformation equations and find this result. So the sigma t factors out, and then the plus kx and the minus kx turns into cosine. So now the spatial part has separated from the time part. What does it look like? It looks like this. You can see that there's a cosine wave that's just growing in amplitude. So the crests are becoming troughs, are becoming crests, are becoming troughs, and these locations that are in between are not moving at all. Those are called the nodes, and then the crest trough part is called the antinode. It's a special example. If we had periodically forced this, we might find what's called resonance, which is a way that waves get excited over and over again. We'll talk about that in a second. The wave equation we talked about, this first one and second one, are not the only wave equations. We could have ones that are appropriate for 2D or 3D, like these next ones below, or in fact this crazy one in line E is actually the Rossby wave equation, and we'll have a sense of that, but you can see beta is the planetary beta, and there's a Laplacian in here which seems to be in totally the wrong place, but it still has a dispersion relation, sigma equals minus beta k over k squared, that sort of looks like the other ones. It means something very weird in this case. It actually means that all Rossby wave phases propagate westward only. Okay, so if a wave is either a standing wave or it's just periodically transiting an entire basin, if the time scale of the transit is such that the forcing of that wave just keeps hitting it and making it bigger every time it goes around, then the response to that particular wave gets large. It's like pushing somebody on a swing. If you push in phase with the swing, they go higher and higher and higher. It's fun to push not in phase with the swing if you really want to mess with the kid, and then they don't necessarily get higher and they get angry. But anyway, this is the kind of thing that makes tides big in some locations. The Bay of Fundy has a wave that propagates right around it, just in phase with the lunar tide. We can extend the notion of wavelength, wave number, to 2 dimensions just as well, and sometimes we have k as a vector, and then we have, with components L and k is the normal notation. So instead of kx, we have k dotted, k the vector dotted into x the vector, or little kx plus ly minus sigma t is the phase function. Okay, let's look at some more movies, and now 2D waves and see what we get. Here's a plunger. So I set up these numerical simulations with either plungers to drive a periodic signal over a certain footprint, or just a blob that I just initialize that's out and let it spread out. So in the plunger case, you can see that the waves are just moving out circularly from the original plunger. No surprise there. You can't really see the little arrows, but they're doing something interesting that we're not going to talk about right now. If I put the plunger in a channel, you get what you expect. So we get circles to begin with. They get to the wall, they reflect a little bit, and they become more linear as they're superposing the reflected wave with the propagating wave. And over time, they get more and more linear as they get farther and farther away from the original circular feature. This is probably what you would guess. If I had asked you to draw these crests and troughs, you probably would have done a decent job in both of these cases. What happens if the channel is rotating? Totally different. Now we see this weird symmetry breaking where the wave along the boundary only propagates in one direction. It doesn't propagate symmetrically to the left and right. It only propagates one way or the other. This is our first introduction to the Kelvin wave. Kelvin, the same guy as the temperature guy, did a lot of cool stuff, did this, discovered this solution of the waves. This is like a hybrid between a surface gravity wave and a geostrophic flow. We'll see about that when we get to El Nino. This is an important part of El Nino. if I put the plunger over near one sidewall, we don't get the far sidewall excited very much, but we get the near sidewall excited in only one direction, which is also very odd. Brad Marston over in physics has been writing papers about this. This is an example in physicist lingo of a topological insulator, which is a topic that won the Nobel Prize in physics just a few years ago. The geophysicists Kelvin knew about this 100 years ago, but that's that. Okay, what if we're in a rotating domain? Now we start to see that we have the Coriolis force, so on this wave as it's propagating, it's kind of spiraling outward. This really is an example of that inertial gravity wave that I talked about before to begin with, where it's both an inertial oscillation, so rotating, watch the vectors, rotating vectors, but also propagating on a gravity wave. But look at this, what's left behind? So we started out with a sea surface high here, and this is a northern hemisphere rotation, and it's still there. Not wave-like at all, it's just a steady feature. So some of that sea surface high tried to escape, started rotating, set up a Coriolis force that pushes back against the pressure gradient and becomes an anticyclone. So this is related to the questions we had today about how the gyre spins up. If you weren't in equilibrium with the equilibrium state of the gyre that has the wind-driven flow and the western boundary current, it could propagate away waves like this and set up a gyre in its absence. And these structures, once they form, the cyclones and anticyclones, are at least stable to wave dynamics because the Coriolis force and the pressure gradient force is in balance. Do the same thing in the channel. We get a blob that stays put. We get Kelvin waves that run away at the beginning. But actually this is a beta plane channel, and so it actually drifts very slowly to the west. Remember, like I said, the Rossby wave dispersion relationship that we mentioned a few slides back has a westward phase propagation. We'll come back to this and start to see how it relates to El Nino and altimeter signals. There's one more thing which Anna is intimately familiar with, which is the geostrophic adjustment case. That's when you start with an anomaly like this, where there's high water on one side, low water on the other. What happens? Well, the high water runs to the low water. But if it does it in the presence of a rotating system, it's actually going to drive flow into and out of the board. And eventually it ends up with a smoother but stabilized front. You get something like this, which has a velocity field like this associated with it. So flow into and out of the page so that the Coriolis force on the velocity field is actually in balance with the pressure gradient force on the final height. This length scale over which this anomaly occurs is governed by something called the Rossby deformation radius, which is this parameter right here. One last thing that's useful to think about as we think about the wave paper is the concept of a Hob Muler diagram. This is a diagram which has spatial dimension on one axis. This is actually east to west, so this is longitude, and then time on a different axis. So if there's a propagating signal, it will tend to go either to one direction or the other. So this has westward propagating signals. This happens to be sea surface height. Westward propagating phase lines. This is a Rossby wave propagating westward in time. At different at other latitudes, which are shown in the other panels, it propagates at a different rate. Slower the farther up you go, faster down here in this bottom panel. Cool. This is from a paper called Shelton and Slacks, which hopefully we'll have a chance to discuss more in class. All right. Thanks very much. See you on Thursday.